going on? Where are you right now in terms of the summer homework? Use your hands here. I see 2, see 4. Okay, this is compulsory voting. You have to vote here. I see a 4. 0 is you don't understand. 5 is you do. What do you think? Summer homework. What do you think? Everybody's got to vote here. Everybody's got to vote. 4-ish. Okay, that's good. If I see 5s, I worry. If I see 0s, I worry. So it's good. So let's make you feel a little more comfortable. Does that sound good? Sequence. Who has seen this word before? Right here. Who's seen that word before? Sequence. Sequence. Oh, come on. Everybody should be raising their hand now. Sequence. Yeah, yeah. Do all sequences have to be infinite? No. They could be what? Finite. What's the key thing that makes something a sequence and not a series? What's something that makes it a sequence and not a series? What's the thing between the terms? A what? Well, the dot, dot, dot is right here, but what's between all of these? What's that? Commas. So there's no operation in the sequence as it is listed. It is just there. Everybody sees what's going on there? Oh, that's nice. It is currently delayed. That's a plus. Have it? Wiley, what do you got?
0, 3 over 2,
Yep.
3 over 3, 5 over 4.
Wait, hold on. 3 over 2, what? 2 over 3?
2 over 3.
Yep.
5 over 4.
Yep.
4 over 5. 7 over 6.
Nice. Who agrees? Anybody agree? Hey, you're popular. Fantastic. Nice. Okay, so this is one direction we can go in. We could have the definition, and we could go forward. What's your question? Did you have a question? Oh, okay. What's the other direction we could go in? We have the equation. We get the sequence. The other direction is I could give you and you have to find the definition, the equation, the definition. What type of definition is this for the sequence? There's 2 types. I haven't said it yet, but you might know what the 2 types are. Oh, that is a type of sequence. That is a type, true, but I'm looking for something a little more general. Yeah. Explicit. These are explicit. These are explicitly defined because when you take n, it gives you the nth. You only need the number n to get the nth entry. What's the other one called? Anybody remember? It begins with an R. Recursive, yeah, recursive definition. We're going to get to that in a second, but these are explicit. So these 2 right here are sequences. I would like you to find the explicit definition for each of them. Find me the explicit. First one, what do you think? 2 to the what? 2 to the what? Yeah, 2 to the n minus 1. What about this one? What's one thing you could do first to make this a lot easier on you? Yeah, put 7 on top. Where you can clean things up. Math is the study of patterns. It's effectively what math is, right? So if you see something that breaks the pattern, see if there's something you can do that makes it fit the pattern, or at least make it fit the pattern a little better. So what's that, 7 over 14? Does that make it a little more identifiable? Well, definitely the numerator is going to be 7. And then what do you notice about these numbers here? There's a gap of 3. That's right. That's one way to look at it. Yep. 1 less than powers of 3 is another way to look at it. See the gap of 3, multiples of 3 are going to be in there somewhere, right? So what's one way you could write the denominator? Anybody have one way? Just 3n what?
Minus 1.
Exactly. Multiple of 3 minus 1. Absolutely. Fantastic. Here's one thing that's really key to realize. If I have 2 points, how many unique lines go through those 2 points? Lines.
No,
1. So I was very strict with the word line linear. There's only 1 line, right? But what happens if I said, you already got a jump on me there, Ian, how many functions go through those 2 points? As many as you want. There's many, right? The point is, this is one mapping we've come up for each one, right? What are the points here? Well, 1 goes to 1, 2 goes to 2, 3 goes to 4, 4 goes to 8, 5 goes to 16, and 6 goes to what? 32. How many functions theoretically go through those 6 points? Infinite. This is the straightforward one, but are there probably an infinite number? Yeah, well, there actually are an infinite number of explicit formulas. This is just a clean, nice one that we can find, that we are programmed to see. I just want you to realize it. Now, we can list out the numbers. We can also visualize them in a couple different ways. This is the same sequence visualized in 2 dimensions and visualized in 1 dimension. What do you have going on here? Oh look. What could you say if you saw this picture? What could you infer? What do you see? It's what? Converging. Looks like it's converging on what? Looks like it's converging on 1. Here's the same sequence. Instead of going up and down, it's going side to side. The first, the second, the third, the fourth, the fifth, sixth. Looks like it's going to 1. So there are 2- and 3-dimensional ways to represent sequences. that will have their usages. That will have their usages. Okay, so what I'd like you to do now, stand up, everybody. What's the way to cheat? Well, you kind of force the squaring. You force the squaring, and you have something to easily build it off of. So the first one here, let's just write down this recursive definition right here. I think you guys had 2 times something. What was it? Sn minus 1 plus 1. You see that right there? Oh, you can't actually see that right there. Sorry. Do you see how I wrote Sn equals? You need to write the whole sentence. Sometimes people, I saw this, like 2n minus 1 plus 1. Is that correct? No, you need S sub n minus 1. You have to be really careful about it. Write the whole phrase. You need the equals. What am I asking you for? Give me what I'm asking you for. Over here, this is 1 squared, that's 2 squared, that's 3 squared, that's 4 squared, that's 5 squared, right? But that would be an explicit formula if you just said n squared. But you're still really close, because what you need to build, what are you trying to build? You're trying to build these bases. So how do you build each of these bases? So how do you build 5 based on 16? How do you build 4 based on 9? How do you get 3 from 4? Consistently, what? Square root it and then what? Plus 1. So once you see these things, sometimes they really pop. So you're going to say S sub n is equal to the square root of Sn minus 1 plus what? 1, then what? Then what? Wiley, then what? Squared. So it feels like it's cheating, but it's not. That is a recursive definition. You take the prior term, you square root it, and then what do? Add 1 and square it. It is technically a recursive definition. So can sometimes the explicit definition can sometimes help inform the recursive definition. Another key facet is that just because something is simple to understand or simple to ask doesn't mean it's a simple question. Some of the simplest things to state are very, very, very hard to prove. You might remember in one of my assembly presentations I asked about, you've seen this. The cube thing is another one, but that's a good memory. 3 squared plus 4 squared is what? 5 squared, right? And 5 squared plus 12 squared is, anybody know? 13. Yeah, these are Pythagorean triples. How many are there? There's an infinite number of them. Nice. But then that guy, Fermat, he made this theorem where if n is greater than 2 and a, b, c, and n are all positive integers, there are no solutions. Like there's no Pythagorean triple for cubics, or fourth, or fifth, or sixth. And he wrote in the margin of his book, I have a proof for this, but I don't have enough space to put it here. People kept on looking. For 350 years, they kept on looking and looking and looking, and they came to the conclusion he was either wrong about what he thought he knew, or he just didn't have a solution. Most likely he had something and wasn't correct in his math. Andrew Wiles spent 7 years privately working on this and solved it in 1999. His proof is over 300 pages long, and there's probably like 200 people in the world that understand it. Is it viewed as correct? Yes. He won the $1 million prize, absolutely. But are they still searching for like cleaner ways? Absolutely. Is this a simple question to ask? Yes. Did it take centuries to solve? So just because something is elegant even in its just solution doesn't mean that it was really hard to get from there to there. I can also tweak sequences by a little tiny bit and change them from straightforward to almost impossible. So just keep that in mind. It's not always easy to know which ones are easy and which ones are hard. Not always. But let's play around with it a little more, shall we? Let's play around with it a little more. So, let me go back up here. Chapter 9. I gave you all of chapter 9. I think I told you that, right? I gave you all of chapter 9. Did I tell you that? Yes, I did? Okay. So this is what I'd like you to do. Go back to the board, please. Back to the boards, everybody. New groups. Find new groups. New groups.
Yeah.
Sure. Joe, Ba, Chi. 5 4 3 2 ling ling。
Wait, 2 people or?
对。
好。
I think so. So number 7. Who has one for number 7 that I think is correct? Who has 7? Yeah, what do you get, Chip?
I got 2 times 2 to the n.
Yeah, so 2 times 2 to the n. Another way to write that is just 2 to the n plus 1 if you wanted to. Either way, totally fine. What about 8? Who has 8 for me? 8. What types of numbers are those? I guess it doesn't matter. It helps me, but what do you have for 8? Who has 8? So Sn is equal to what? Oh, 2 to the n what? Yeah, so you saw they're all powers of 2 minus 1. I like that. 9 gets a little more interesting. You have 2, 5, 10. Something's going on there. Oh, it's 1 greater than what? Squares. So you have Sn equals what? Yeah, n squared plus 1. What about 10? What do you see there? Those are the what numbers? If you ignore the negative signs, what are they?
Squares minus.
On 10. Not square. What are those numbers called? There's a 2n minus 1. You see the numbers? Yeah. So you have what there? It's changing signs, so you know there's going to have to be a negative 1 to a certain power. Correct?
Yeah.
And then you have 2 times n minus 1. What should the power of the negative 1 be?
N minus 1.
Or n what?
Plus.
Either one works, right? You just have to offset it by 1. You could also you could put the negative somewhere else if you wanted to. Yes. But it has to alternate. So you're saying on 10, no, you did it right. Yeah, n minus 1. That's fine. Yeah, you can either n plus 1 or n minus 1 is totally fine because n is starting at 1. 11. Well, that's nice. 1, 2, 3, 4, 5. So what's the numerator? What's the numerator? N. Hey, there's a bid. And then it goes 3, 5, 7, 9, 11.
2n minus 1.
2n minus 1. Excellent. And what about 12? I like Shirley, how she put, I like Shirley's, it's actually wrong?
It should be times 1, 2, 0.
Well, doesn't it flip already with the negative 1 that's in there?
No, but now those 1 over 2n.
Oh, it'll do the 1 over 2n. It'll multiply, it'll bring that to the power. So it's negative 1 to the n plus 1 times what? 1 over 2n. Oh, I see. You put the 1 over 2n on the inside, so it brought the power along too. Well, I did like it. I thought it was eloquent, so we'll have to spot check it. Yes, definitely 2n plus 1.